In this video, we're going to look at the definition and trend in ionization energy across the periodic table. The definition of ionization energy would be the amount of energy required to remove an electron from the ground state of an atom or an ion. And more importantly, we have to clarify that this is in the gas phase. So, how applicable is this idea? Not super, but it does help us to understand some of the common ions of the elements in the periodic table. As an example, we can look at a generic metal denoted by the letter M in the gas phase undergoing this change to produce a cation. So if we lose an electron, we're going to become positively charged, and that free electron. This reaction is going to require some energy. And I want you to think about this. Is this energy going to be positive or negative? And so remember what the energy sign tells us. Energy that's positive, we have to put energy in. So do we have to put energy in to remove that electron? Or is energy going to come out? When we remove that electron, is energy going to be released? So think about that and answer this question. So it turns out this change in energy will always be positive for ionization energy. And the reason is because we have that attractive force between the nucleus, positively charged, and the electron, negatively charged. And to overcome that attractive force, we have to put in energy. And if you recall back to the Bohr model, and when we put electrons into an orbital, energy is released. So this is the opposite. We're removing an electron from orbital, and so that energy will be positive. So ionization energy is always positive, greater than 0. And this change in energy we define as the ionization energy. And I'll put a little subscript 1 because it's the first ionization energy. It's the energy required to remove that first electron. We could go on and say, well, we could lose another electron from this metal ion to give a 2+ cation in the gas phase, plus another electron. The change in energy here would be ionization energy 2. And we could do it X number of additional times to give additional ions plus electrons, and this change in energy is ionization energy 3. Now, what do you think is going to happen in terms of these values as we go from IE1 to IE2 to IE3? Are we going to increase? Is it going to get more positive? Or are we going to decrease these numbers? So is it going to get easier or harder to remove an electron as we remove additional ones? As you might imagine, it's going to get harder and harder because as we increase this charge, it becomes less and less happy. So ionization energy 1 will always be the smallest positive number, and we increase going to IE2 and increase even more to IE3. Let's look at a specific example of successive ionization energies. Let's first look at sodium. Sodium requires a little bit of energy to remove that electron from the 3s orbital. At that point, sodium has a noble gas configuration. It has a filled outer shell. So to remove a second electron, we see a huge jump in ionization energy. It's about 10 times more energy to remove a second electron than it was to remove just the first electron. And the reason is because these core electrons are much harder to remove because they are part of this filled, exceptionally stable outer shell. Now, if we move to magnesium next door, we see that it requires some energy to remove the first electron, a little bit more to remove the second electron, about twice as much, and then about 4 times more to remove that third electron. And that is another big jump from the second to the third because we're removing a core electron from a filled shell. It is always going to be true that ionization energy will increase as we remove additional electrons, and we will always reach some big step when we remove a core electron. Now, what is the trend in ionization energy that we need to know? Let's first look at the ionization energy trend within a group. From this plot, you can see that ionization energy decreases as atomic number increases. So as we move down the group, ionization energy is decreasing. So why? The big question I always like to ask. We have to think about this with respect to those electrons. Those electrons in higher n levels are farther from the nucleus. So we have a larger distance. According to Coulomb's law, the energy of attraction there is going to be smaller. So we need to put energy in, a smaller amount of energy in, to remove an electron that is in a higher n shell. So as my atom size increases, my ionization energy decreases. We can look at a different plot and understand the trend across a period. Within the period, we can relate it back to effective nuclear charge and also atomic radius. So we know effective nuclear charge increases across the period. We have more protons, those electrons are held more tightly, so we have smaller atoms. And as a consequence of both of those ideas, we have larger ionization energies. And we can see that general trend, ionization energy increasing as we go across the period. There are several exceptions, which we'll get to in a later video. The idea that effective nuclear charge is increasing, it's holding those electrons more tightly. We need more energy, higher ionization energy, to remove an electron. That electron is also closer to the nucleus, so we have a smaller distance, greater attractive force. Thinking about it with respect to that, we also need more energy. When we think with respect to atomic radius, we have a smaller atom, that electron is closer to the nucleus. Relating to Coulomb's law again, smaller distance, larger energy released, more energy would need to be put in to remove that electron. That's the trend in ionization energy. Thanks for watching.